boogie.
This last short video of this lecture is really set up for a first big thing that we're going to do in the next lecture. So what we're going to do is prove the first part of proposition 21 here and finish the proof of proposition 21 in the next lecture. So let's say that K1 and K2 are Galois extensions of a field F. We're going to prove that intersections and composites of Galois extensions are Galois extensions. That is, K1 intersect K2 is Galois over F, and the composite of K1 and K2 is Galois over F. All right, let's do it. First, let's do intersections. So what we're going to do is we're going to show that if you have an irreducible polynomial in F bracket x, P of x, that has a root in K1 intersect K2, then all of the roots of P of x are in K1 intersect K2. That is, we're showing that K1 intersect K2 is a normal extension of F using this definition of normal that is used in Conrad's notes and many other sources, but isn't stated this way in Dummett and Foote. Okay, so what does that get us? Since K1 over F is a Galois extension, it's a separable extension. So K1 intersect K2 is a subfield of F. A subfield of a separable extension is separable. So K1 intersect K2 is a separable extension of F. And we proved in lecture 19 that this definition of normal, that if you have an irreducible polynomial that has one root in your field, then all of the roots lie in the field. Normal plus separable is equivalent to being Galois. So this is stated and proved clearly in Conrad's notes. It's not stated and proved clearly this way in Dummett and Foote, but we did prove this in lecture 19. Okay, so all we have to do is show that if you have an irreducible polynomial in F bracket x that has a root in K1 intersects K2, then all of the roots are in K1 intersects K2. Okay, so let's name a root of this irreducible polynomial, let's say alpha in K1 intersects K2. So it's a root of this irreducible polynomial P of x. All right, so alpha is in K1, certainly, because it's in K1 intersect K2. And K1 over F is Galois, so it's normal. So all of the roots of P of x are in K1. And now exactly the same thing, switching K1 and K2. Since alpha is in K2 and K2 over F is Galois, all of the roots of P of x are in K2. But that means that all of the roots of P of x are in K1 and they're in K2. So they're in the intersection of K1 and K2. Okay, so K1 intersects K2 is a normal extension of F. It's separable, therefore it's Galois. All right, let's prove the second part, that the composite is Galois. K1 is a splitting field of some separable polynomial, let's say F1 of x in F bracket x. This is one of the equivalent conditions of being Galois, is that you are the splitting field of a separable polynomial. K2 is the splitting field of some separable polynomial, F2 of x in F bracket x. So their composite is the splitting field of the square free part of the product over F. So we have to take the square free part because we want this product to have distinct roots in a splitting field. We want this polynomial to be separable. So we'll take the square free part. This is something that we've already seen, like in the proof of theorem 13, for example. And why is this splitting field? Well, think about, where does K1 come from? It is F adjoin all of the roots of this polynomial, F1 of x. K2 is F adjoin all of the roots of this polynomial, F2 of x. So you take those special set of algebraic elements over F. There might be some repeats between them. The square free part might not be the product. There really might be repeated roots, but you just take the set of those roots that are distinct, and the composite contains all of those roots. It's the field generated over F by the set of distinct roots of this product, F1 of x times F2 of x over F. So okay, now K1, K2 is the splitting field over F of a separable polynomial in F bracket x. K1, K2 is Galois over F. Okay. What is the Galois group of K1 intersect K2 over F in terms of the Galois groups of K1 over F and K2 over F? Well, the fundamental theorem of Galois theory tells us about that. I mean, you have K1 over F is Galois. K1 intersect K2 is also a subfield of K1 that is Galois over F. So if you take the fixed field, or you take the subgroup of the Galois group of K1 over F corresponding to this intermediate field K1 intersects K2 and call that H, now we can understand the Galois group of this intermediate field in terms of the whole Galois group and that subgroup H. So you should really think carefully about how to use the fundamental theorem to say what the Galois group of K1 intersects K2 over F is. What is the Galois group of this Galois extension, the composite of K1 and K2 over F? Not so clear how to use the Galois group of K1 over F and the Galois group of K2 over F to describe this Galois group of this bigger extension. So this is where we'll start in the next lecture.